Good day, everybody. This is Peter Clark from xSeriCon, and I'd like to wish you a very warm welcome to our webinar. This is the latest in our ongoing series of monthly webinars on process safety related topics. Today, the topic is about proof testing of safety instrumented functions. A little bit about myself first. So I'm the Managing Director of xSeriCon, which is a small safety consultancy based in Asia Pacific, and we specialize in all kinds of process hazards analysis, such as HAZOP and SIL, alarm management studies, RAM study, and anything to do with functional safety. So we cover the full functional safety life cycle. So first of all, let's introduce what we mean by proof testing. And even before that, we need to take one more step back and say, what is it that we're proof testing? So today we're focusing on something called a safety instrumented function, or SIF, which is a function that is completely automatic, and it's designed to detect when a hazardous condition arises in some process equipment and take an action in order to achieve or maintain a safe state in that equipment, with the intent of avoiding or minimizing some harm that may arise, such as an overpressure or overfilling, a loss of containment, a spill that could lead to a fire or explosion, or an injury, or an environmental incident. So an example of a SIF would be a sensor that's provided to detect high level in a storage tank. And when that high level is detected, the SIF will automatically close an isolation valve at the inlet of the tank in order to maintain a safe level in the tank. So much for what a SIF is. So what do we mean by proof testing? Well, proof testing is a manual test that is performed by a person, not automatically by the system. And it's designed to be carried out on a fixed regular interval. And it consists of a functional test and usually an inspection as well, with the intent being to try to determine whether certain specific dangerous failure modes have occurred since the last time the function was tested. So we've used the term there, dangerous failure. What do we actually mean by a dangerous failure? Well, in SIF terms, a dangerous failure is a failure that makes the equipment in the SIF unable to achieve its design intent. And its design intent is to detect the hazardous condition and to transition or maintain the process into the designated safe state, which, for the example that we just gave, would be to prevent overfilling of the tank. So we usually distinguish between the ways in which the equipment can fail, and the two main categories that we consider are dangerous failures, and the other one we call safe failures. Now, safe failures, which actually are not that relevant to today's talk, but just for the sake of completeness, a safe failure is a failure that will normally lead directly to a spurious trip of the safety function. In other words, it makes the safety function think that the hazardous condition has occurred, but even though it actually hasn't, and causes the safety function to take its action unnecessarily, which of course usually leads to some kind of disruption, such as process downtime. But today we're more interested in the other kind of failure mode, which is called dangerous failure, which, as I said, is a failure that makes the SIF either unable to detect the hazard, or if it does detect the hazard, it's unable to take the necessary action to put the process into the safe state. And to understand how this relates to proof testing, we need to distinguish between some different kinds of dangerous failures. And here at xSeriCon, we use this terminology that you can see on the slide now. There are usually two different ways of detecting whether dangerous failures have occurred. One of them is by proof testing, which, as we've just said, is a manual test, and the other is by some automated testing, which usually is called diagnostics. Any kind of failure mode that the system can experience, because any system has got multiple different ways of failing. For example, if we're talking about a spring return actuator on a shutdown valve, it could fail by some problem with the air supply. It could be a spring related. It could be mechanically stuck in position. There could be a problem with the Scotch yoke. There could be a problem with the exhaust valve, multiple different ways in which it could fail. Now, some of those could be detected by some automated diagnostics, such as an automated partial stroke test. And those failures, we call those detectable failures. Other failures may not be detectable by the diagnostics, but still might be detectable if we do a manual test. And the manual test can test more different failure modes than the diagnostics. If that were not the case, then there would be no point in doing the manual test. You might as well only do the diagnostics. So those tests, those kinds of failures in xSeriCon, we call them discoverable failures. There is some confusion in the industry among what is meant by the term detectable failure, because some people use the term detectable to mean detectable by proof test. But that's confusing, because we should be using the term detectable only to talk about failure modes that can be detected by diagnostics. So in order to avoid that confusion in xSeriCon, we call failures that can be found with diagnostics detectable, and failures that cannot be found by diagnostics but can be found by proof testing, we call them discoverable. And that corresponds to the orange slice in the pie chart that you can see on the right of the screen. And then there's a third group which might not be detectable at all by any kind of testing, neither by proof testing nor by diagnostics, and those we call undetectable failures. And you can see those in the blue slice of the pie chart. And in a few moments, you'll see why it's important to distinguish between those failure modes. So just to emphasize again, the purpose of doing the proof testing is really to find out whether those discoverable failures have occurred. It is not to actually prove that the SIF is capable of working. As we've just said, some of the tests, some of the failure modes may be undetectable. They might be in that blue slice of the pie chart that we saw there. And then no amount of testing is going to prove that whether or not those failure modes have occurred. So we can never demonstrate that the SIF is actually working just by proof testing. All we can demonstrate is that certain discoverable failure modes have not occurred at the moment at which we do the test. And then, of course, as soon as we walk away, those failures may actually have occurred during the time since the last test. So there is a gradually accumulating probability that failures have occurred since the last test. So all we can do is kind of reset the probability of those failures having occurred back down to zero. And that's what we're trying to achieve with proof testing. So why do we care about proof testing? Why is it necessary to do it? Well, there are quite a lot of reasons. One of them is that in the teal colored blocks at the top of the screen, if we include proof testing in our calculation of the predicted probability of failure on demand of the SIF, then proof testing does reduce the probability of failure on demand and therefore improves the integrity of the SIF. Now, as I'll show you a little bit later, it actually doesn't have that dramatic an impact. It's not going to move you, for example, from a SIL 1 to a SIL 3 function, but it does have some worthwhile impact on the availability of the SIF. The second reason is that regulatory bodies may demand or insist that you perform proof testing. And this was one of the lessons that was learned from the Buncefield incident, which, in case you're not familiar with it, to me, it's in my top 10 list of incidents that every process safety practitioner should know about. It was in the UK about 15 years ago. It was an incident involving overfilling of a fuel storage tank at a fuel storage depot in the south of England. And by an amazing miracle, there were no serious injuries or fatalities from the incident. mainly because it happened on a Sunday morning when very few people were around. One of the lessons learned from it was that although SIFs were provided, or safety functions, should we say, were provided that should have detected and prevented the overfilling of the tank, they didn't work. And the subsequent investigation found that it was virtually impossible to proof test those safety functions because the high-level sensor was located in such a position that it wasn't actually accessible for proof testing, and it was designed, it was configured in such a way that no one could have ever proof tested it. So that was one of the outcomes in the investigators' report from the Buncefield incident, that it should be possible. SIFs should be designed in such a way to make it possible to proof test them. Another reason for doing proof testing is that it's stated as a requirement of the functional safety standard that applies to the process industry, which is IEC 61511. If you want to see specifically where that is, Part 1, Clause 16.3 says that safety functions shall be proof tested. And a fourth good reason for doing proof testing is it means that we actually pay attention on a regular basis to all of our SIFs, and we don't just basically install them and then forget them. And one of the reasons why it's good to revisit them from time to time is it gives us a chance to discover potential problems caused by human errors, which can lead to what we call systematic failures. Now, an example of that would be, let's say that there was some problem on the plant, or we were doing some startup or some abnormal operation, which necessitated us putting a bypass or override on a safety function. And although we should have procedures in place to make sure that that bypass doesn't get left behind and forgotten accidentally, it may not work, the procedure may not work, something may go wrong, and as a result, it could be that the function is left inadvertently overridden. And that should be picked up when we come back to do the proof testing, because if you proof test a function that's overridden, hopefully the function will not act, and then it will raise an alert for further investigation. So that's another good reason why proof testing is worthwhile. Now, I mentioned a moment ago that proof testing does reduce the PFD, the probability of failure on demand of the safety function. And just to explain that in a little bit more detail, to put it in a simple way, the probability of failure on demand of a safety function has got three main contributions to it. The first one that you can see indicated by the number 1 on this graph arises from the undiscoverable failure modes. And that's the gradually rising gray dotted line at the bottom of the graph. So as you can see, over time, as we move from left to right, the probability that those undiscoverable failures have occurred gradually increases over the entire lifetime of the function. There's nothing we can do to get rid of those unless we actually refurbish or replace the equipment. So that is an underlying, gradually creeping up baseline of probability of failure. And the proof testing can do nothing about that. Then contribution number 2, you can see in the orange circle, arises from the fact that the function normally needs to be bypassed in some way during proof testing. So there are these little short intervals that occur every time we proof test. Let's say the proof test lasts for 2 hours and we do it once a year. That means that there is this little window of time for 2 hours once a year when the function is guaranteed to fail because we deliberately bypassed it. So that's why we have these spikes on the graph. And the reason why it's important to think about those, you'll see in a moment or two. And then number 3, the blue circle, is the discoverable failures. And these are the failures that the proof testing can discover. And when we discover them, then of course we will fix them and get rid of them. So you see that there's a little sloping line that goes from 0 up to 1 year, underneath which is just sitting on top of the shaded area of the graph. And then when we do the proof testing, we discover any of those discoverable failures that have occurred. We fix them, and it means that that little bit of increase drops back down to the baseline again. So that's why you get this kind of sawtooth shape where it goes, the probability goes up. We do the proof test, that brings the probability back down again to the baseline. And then until the next proof test, it gradually creeps up again. We do the second proof test, it drops down again, and so on. And that repeats through the whole lifetime of the SIF. And what we're doing by proof testing is we're bringing that component of the PFD average, which is the number 3 component, back down to the baseline. If we did not do the proof testing, then we wouldn't get back down to the baseline, and that shaded area would gradually build up and up and up and become quite large over the whole lifetime of the SIF. And as a result, the average PFD averaged over the whole lifetime, which is the total area under this black curve, would be higher if we do not do the proof test than it will be if we do the proof test. Now, how much impact does it really make? Well, just to give you some idea of a typical safety function. So I dug up a SIF from a recent analysis that we did for a client, whereby the client asked us to consider proof testing at an interval of 12 months. And the result came out, this was for a SIL2 SIF. The PFD average for that was 1.4 times 10 to the minus 3. So that's a kind of pretty lowish, I mean, quite a, should we say, high performing SIL2 rated SIF. Then just as an experiment, we went back into the software and we removed the proof testing and saw how much difference it makes. And what happens was the PFD average increases from 1.4 times 10 to the minus 3 to 4.1 times 10 to the minus 3, which is roughly a factor of 3 increase. So that's why I said at the beginning, it's not actually a massive effect. It's not like it's changing the PFD average by a factor of 10 or 100. It's only by a factor of 3. And this is a fairly typical result that we see. So it's worth having. I mean, it does make this SIF, 3 times more effective, but it's not going to completely change the performance of the SIF, let's say, from a SIL1 to a SIL3 rated SIF. It's not a kind of a magic bullet for solving all problems. Now, another thing we should be aware of during proof testing is we normally don't only do the test, we also do an inspection as well. And the purpose of inspection is really to see if there is any obvious physical problem with the equipment that the SIF relies on, such as the sensors and the final elements. So we'll be checking, for example, covers on the equipment to make sure that they're properly applied and there's no leaks, no sign of corrosion. We'll be checking that the cables look to be in good condition with no mechanical damage. There's been no collision or impact damage on the cables. All of the seals and glands are tight. No obvious physical damage to any part of the equipment, no obvious corrosion, no obvious fouling. Now, one thing that's important to be aware of is it is important to do the inspection before we do the test. And the reason for that is we are, of course, going to record the result of the test, and it is important to document the condition of the equipment as found. Now, the reason for that is we need to be able to track the occurrence of what we call systematic failures, which means failures that could occur as a result of human errors, basically any cause other than the natural wear and tear on the equipment. And that's important because if we find that the systematic failures are occurring at an unacceptably high rate, which means basically significant relative to the rate of the random hardware failures, the wear and tear rate of failure, then we need to be asking questions about how good our controls are in our inspections and whether we've made some unwarranted assumptions about the availability or the performance of the safety function during the analysis phase. Another thing that can be done, probably should be done, is to confirm that the diagnostics are working during the inspection. And one way that that could be done is to look at the historian and to see whether the diagnostic is actually generating automatic reports saying that the diagnostics were running and that they, they did their tests and they found no faults. Or some kind of indicator. We should be looking for some kind of indicator that diagnostics are actually running as designed. And it's important not to assume that the diagnostics are actually running. For example, supposing the diagnostics are found to give a lot of nuisance alarms, a lot of, should we say, fault reports, which maybe are not genuine faults or are not serious enough to merit further investigation. But it could be that the operator is getting bombarded with a lot of nuisance messages or alarms from the diagnostics. And as a result, you might end up just bypassing or disabling the diagnostics, which obviously then compromises the integrity of the SIF, because it would have been assumed during the analysis phase that the diagnostics were available and running. So that's important to check. And if you are having a problem with a lot of diagnostics alarms, then rather than just disabling them or bypassing them, do some proper investigation and find out what those alarms are really telling you. Now, another thing we need to consider is what is the appropriate proof test interval? Now, the proof test interval, of course, we want it to be in some ways as long as possible, because proof tests are disruptive to the process. They cause disturbance to the equipment, so we should ideally do them as little as possible. They're also expensive because it costs manpower, not only to physically do the test, but also to document the results and to analyze. And you've got to keep people trained and keep their training up to date for doing all of these tests. And there's a certain amount of hazard involved in doing these tests as well, because the maintenance personnel may need to go to remote locations of the plant and climb up ladders and touch equipment that is not normally touched, maybe under pressure, maybe at high temperature. So there's a lot of reasons for trying to minimize the amount of proof testing. However, it is a requirement of the standard that the proof tests need to be executed at least 2 times for every predicted demand on the safety function. So if your calculations, for example, from LOPA, layer of protection analysis, show that you expect a safety function on average to be to have a demand of, let's say, once every 2 years, then that means that your proof test needs to be at least once per year. Otherwise, it's not valid in terms of its ability to, or the likelihood of detecting those discoverable faults before there is an actual demand on the function. So that's a rule that's imposed by the relevant standards, and we need to make sure that that's complied with. Now, the proof test interval doesn't have to be the same for all parts of the safety function. So, for example, the final elements, the shutdown valve, the actuator, the solenoid, may need to be tested more frequently than components such as the sensors. And there could be several reasons for that. One is that they have a higher probability of failure on demand. So you need more proof testing in order to keep that down, basically, to discover those number 3 area on the graph that I showed you a moment ago. This area number 3 would be bigger for less reliable equipment, especially for final elements. Another reason would be because the the sensors and logic solver are more likely to have quite advanced diagnostics in them, which means that the number of the discoverable faults available that cannot be detected by diagnostics actually may be quite small. So the need for proof testing on those, we say more, we call them type B equipment, the equipment with more internal diagnostics, is less. So then you may think, well, in that case, let's do lots and lots of proof testing, and then we can get really good performance from our SIF. But there is another side to the coin, which is if you over test, then that can cause various problems. One of which is that, as we mentioned earlier, the SIF may be unavailable during the test because you have to bypass it. And that unavailability starts to become dominant if you have a very short proof test interval. If you think about it, 2 hours of unavailability per year is not very much because there are 8,000 something hours in a year. But if you're doing a proof test once a month, then 2 hours per month is suddenly quite a large fraction of the total time in the month. It starts to become something like 0.2% of the time that the function becomes unavailable. And that can actually have a significant impact on the PFD average, as you can see in the graph at the bottom of the screen now. You see at the left side of the graph, we go through a minimum point, which is kind of the optimal proof test interval in terms of minimizing the PFD average. But then further to the left of that, as you continue to reduce the proof test interval, the PFD average starts to shoot up. And that's because of the unavailability of the SIF during proof testing. And the other main problem is that the more you test, the more likely you are to make an error and accidentally, for example, leave a bypass in place after testing, or leave a shunt, or leave a wire disconnected, or leave a cover loose, or something. There are all kinds of fault problems that could be experienced. And I don't know if you have come across the writings of Trevor Kletz, who is one of my heroes in the area of process safety. He's written a lot of really excellent books and papers on the subject of some accidents that occurred that could have been avoided by basically doing things differently. And one of the subjects that he covers in some of his books is over testing of equipment, which can lead to exactly these kinds of problems. And he's got case studies of this in those books. So I highly recommend them. Trevor Kletz. Please do check it out if you're not familiar with his work. Okay, now one more question that sometimes comes up relating to proof testing is it necessary to test the entire function in one go? And the answer is no. It is not a requirement of the standard to do end-to-end testing. You can test the function in segments. For example, you can test from the sensor up to the logic solver, up to and including, and then test from the logic solver to the final element. And as long as all of the critical components, all of the components that have potential dangerous failure modes get tested at some point, then the test regime is valid. Now, the next question to think about is, well, actually, what fraction of failure modes can be detected by proof testing? So just skipping back for a moment, we showed this pie chart with some different segments of detectable, discoverable, and undetectable failure modes. Basically, how big is the green and the orange sector? So just to give you a typical idea, the proof test coverage, the term that we use to describe this, is the fraction of dangerous failures, which is measured by this failure rate term lambda. And the dangerous failure rates are lambda D. That's to distinguish them from the safe failures that I mentioned earlier. What fraction of those are discoverable? And bear in mind that that discoverable also includes detectable failures, failures that can be detected by diagnostics. So the typical lambda D value of the discoverable failures for a simple shutdown valve without testing tight shutoff, without testing the tightness of the valve, just basically testing that the valve strokes correctly on demand, is around 0.4. So what we mean by that is the total area of the green and orange areas in that pie chart is roughly 40% of the total pie for that particular device. For a solenoid valve, the solenoid valve that controls the air going to a pneumatic actuator, the discoverable failure proof test coverage is essentially 1. We pretty much can detect all of the potential dangerous failures in that device by doing a typical proof test. And the same goes for a single acting pneumatic actuator. There are very few, if any, failure modes that are not discoverable by a proof test. For a smart transmitter, the proof test coverage that we would normally use in our calculation is around 95%. Actually, the diagnostic coverage of that, by which we mean the fraction of dangerous failures that are detectable by diagnostics, is already pretty high. It's already usually around 90% for those types of device like a smart pressure transmitter. So it's important to use realistic proof test coverage values. Don't just apply the value 1 to everything, which I very often see done, unfortunately. And especially for final elements, be really careful not to be over optimistic with your proof test coverage values for final elements. So where do you get those proof test coverage values from? Well, you can always ask us, because we will provide you with guidance whenever we can. But some source materials that you can use to try to get reasonable values, the kind of gold standard, the best place to get it from is to find the FMEA report relevant to the equipment that you're using. FMEA is failure modes and effects analysis. And this is a type of desktop study that you can do to basically sum up the effects of all of the different failure modes of a device and make an assessment on which of them count as dangerous failures, which of them count as safe failures. And from that, you can calculate a predicted value for the proof test coverage. And that's probably the soundest method of coming up with an accurate and defensible value for the proof test coverage for a device. And you'll find that a lot of manufacturers may make available their FMEA reports. You can often request them from the manufacturer or even download them from the website. That information may also be provided in the safety manual that should be provided by the manufacturer for all equipment that is intended for use in a SIL-rated application. Another place to look is in a previous SIL verification report. So if you've got a report that covers from a previous study that covers the equipment you're looking at, that should state what proof test coverage value was used, and hopefully with some justification for that value. So that would give you an idea of what value to use. But again, I will mention my same warning from before that it's not uncommon, unfortunately, to see a value of 1 assumed across the board for proof test coverage, which is incorrect and over optimistic. So if you see that the SIL verification report has done that, then please do not follow suit. But check what the value should be for yourself. You may also find proof test coverage values provided in failure rate databases. There are quite a few sources where you can get these databases from. As you may know, if you purchase a license for SIL verification software, it may come with a database included, and that is true for our own SIL verification software, which is called SILability. That does come with a database, and the database does have proof test coverage values for certain selected items of equipment where we have enough traceable data to demonstrate that value is reasonable and it's not just a guess. Another thing you can do is, if you can't find a proof test coverage value for the exact device that you're using, try to find something for similar equipment from another manufacturer. So for example, if you're using a trunnion mounted ball valve, To be honest, the failure rate from one manufacturer to another for a SIL-rated ball valve is not going to vary a great deal from one to another. And likewise, the proof test coverage is not going to be that wildly different from one manufacturer to another. So at least it'll give you a reasonable value to use. Now, one thing to watch out for is if you are trying to evaluate whether a proof test coverage value is reasonable, watch out for the diagnostic coverage of the same device. So diagnostic coverage is the fraction of dangerous failures that are detectable by diagnostics. And as we said a moment ago, for smart transmitters, that would be typically around 70, 80, even 90%. Whereas for devices that do not have any built-in diagnostics, then that diagnostic coverage should be 0, of course. Just make sure that the proof test coverage value you are trying to use is more than the diagnostic coverage, and that is kind of stands to reason. It must be higher, because if the proof test coverage is lower than the diagnostic coverage, then it means that there's no point in doing the proof test. You might just as well rely on the diagnostics. What does a proof test procedure actually look like? Here's an example. This is from a textbook that I very much admire and recommend. It's by Grun and Lucchini. It's called Safety Instrumented Systems, published by ISA. And this is an example of a proof test procedure that they provided. So it's a fairly kind of broad brush overview procedure, this, but you can see that it says, first of all, check the calibration of the transmitter. So that means under permit. Now, this is a really important little detail, under permit. So your proof testing needs to be covered by a permit to work procedure. And that's important because every disturbance that is made to the system for the purpose of proof testing, such as applying bypasses, overrides, removing covers, applying shunts, changing set points, changing anything in the settings of the equipment, whether it be the field equipment or the logic solver, needs to be carefully managed and reversed at the end of the procedure. Very important. So that's why the permit to work really needs to cover that carefully. So that's the first thing your proof test procedure should say, is get a permit to work and make sure that it covers all of the changes and captures all of the changes that are made for the purpose of proof testing. And you can see it takes through step by step, checking the calibration of the sensor and then applying test conditions to confirm that the readings are correct. And then it does a simulated test in order to check that the final elements are working, so that it trips, and then reinstate everything and put it all back and document whatever faults are found and repaired. Now, one question that often comes up in the context of proof testing is, what about partial stroke testing of valves? Is that a proof test or is it a diagnostic? Now, the reason this question is important is because it's very often assumed in SIL verification calculations that partial stroke testing is a diagnostic. Because that has should we say, an effect that is desirable on the calculation of the SIL achieved and the risk reduction factor achieved by the SIF. But let's be careful about the rules for what a diagnostic really means. If we want to count any kind of test as a diagnostic, then two things must apply. First of all, the test must be completely automated. It must not be on demand by the operator. It must not rely on the operator or on any other maintenance personnel in any way. It must be completely automatic. with no human intervention required. And normally that would not be the case for partial stroke test, because you don't really want your valves that are critical, part of your critical process operation, to be stroking all by themselves without any operator awareness or the operator even knowing what's going on with those valves. So it's very rarely done that partial stroke testing is automated, at least not so that it actually starts automatically. Sometimes there will be a stroke testing device provided that when the command is given by the operator, then the valve will stroke, for example, from 100% to 80% and then back to 100% again. But that still doesn't count as a diagnostic, because it relies on the operator giving the permission or the command for that stroke test to occur. And the other condition that has to be met according to the standard to qualify as a diagnostic is that the test must be run 100 times per predicted demand rate on the SIF, which basically means frequently. I mean, that means weekly, maybe even daily or even hourly. And that is what is intended really by a diagnostic. It's meant to be something that's in the software, in the programming, and just runs basically all the time. And if those two conditions are not both met, then we cannot consider partial stroke testing to be a diagnostic. It has to be counted as a proof test instead. Now, if we are not counting as a diagnostic, that means that if partial stroke testing was included in the dangerous detectable failure rate, which is very often the case, then that means we should not be counting partial stroke test in those lambda DD, which is dangerous detectable failures. It should be getting added back into the undetectable failure rate. And let me show you what I mean. Here's an example of a little extract from a SIL certificate produced by Exeter. You can see that it contains 12 rows of failure rates in total. The first 3 rows are for without partial stroke testing, and then the next 3 rows are with partial stroke testing. And what they've done for the with partial stroke testing values is they've deducted 196 from the lambda DU and counted that separately as a lambda DD. And that is valid only if the partial stroke test is a diagnostic. If it is not a diagnostic, then you have to add that back into the lambda DU, which basically gives you the same lambda DU values as you got in rows 1, 2, and 3. So watch out for that, because that will give you an optimistic result in the calculation. If you don't take account of that, then basically those values will disappear. Remember back this graph that I showed you before. If you count those as lambda DDs, it means they will not contribute to area 3 of the graph, which means that then you're doing an over-optimistic calculation. And previously we showed that the impact of including or excluding proof testing can be around a factor of 3 times on the PFD average value. So if you incorrectly count those lambdas as DDs when they should really be DUs, then you are miscalculating potentially by a factor of 3 the lambda, the probability of failure on demand that you can actually achieve with the SIF. So please do be careful about that. That is a pitfall that I very often see in the industry. Okay, one last thing to say about proof testing is record keeping. It's very important that records are available to demonstrate that proof testing has been completed. You need to confirm what was tested, using what testing method, what the results were, of course, when it was done, so that we can confirm that the schedule is being kept up to, and also, importantly, who is doing the proof testing. Now, the reason for that is relating to the competency requirements. I frequently do functional safety assessment and functional safety audit. And one of the things I'm always looking for and asking about is, show me the evidence that you've got that the personnel who are doing functional safety related tasks, including proof testing, are proven to be competent for those tasks. And I'm going to need to see evidence of who is doing the proof testing and how do you know that they are competent for that task. So that's why record keeping is important for the functional safety assessment and functional safety audit. Another reason why it's important is because you need to keep records of how well the safety function is actually performing in terms of what are the observed failure rates of the device, and also whether you are seeing an unacceptably large number of systematic failures that means failures caused by human error, such as leaving a bypass in place. And that's important because the standard requires you to do a comparison or do a measurement of the actual observed performance of the safety function compared with what you assumed it was going to be during the analytical phase. And you need to do that in order to validate those assumptions that were made. And if it turns out that those assumptions were over optimistic, then you need to reassess the level of risk reduction that your safety functions are actually providing and see whether it's enough to meet your tolerable risk target. And another useful reason for recording the proof testing carefully is it allows you to compare with the results of your RAM study, because your RAM study and proof testing are tied up together. Your RAM study would be assuming a certain amount of performance from your safety functions. It would be assuming a certain amount of downtime for proof testing, and it would be assuming a certain amount of labor requirement for proof testing as well. So let's say, for example, you assumed that your proof testing was going to take 2 hours each time, that your safety functions would be bypassed for 2 hours, but it actually turns out to be taking longer than that for some reason, then that's going to impact on your RAM study results and on your SIL verification results as well. One final suggestion I would like to make is try to avoid having all the proof tests done by the same team or by the same person. Now, the reason for that is if you have only one person or one team always doing all the tests, there may be some point where they maybe are not doing it correctly, maybe due to a misunderstanding. Maybe they are cutting corners. Maybe they are actually just filling in the checklist to say that they've done the test, but they're not actually really doing it. Or they're skipping some important points. And that might go on for years and not be discovered if you don't have any diversity in your team. You don't have different people. Maybe you need to rotate your teams around different areas, or even do some spot checks from a different team, maybe from a different plant. All helps you to increase the chances of discovering those systematic failures. Right, that's the end of what we wanted to say today about proof testing. So I want to thank you very much for your attention. If you have a question, then please feel free to ask now. You can unmute your mic and ask, or you can put a question in the chat box. So please go ahead and do that now. You can also email us afterwards, tell us any questions that you have, and I'll get back to you as quickly as possible. Also tell us if the webinar was useful, and you can mention any other webinar topics relating to process safety, process hazard analysis, functional safety that you might like us to cover in the future. As you know, we have quite a lot of previously recorded webinars available on our YouTube channel. So you can just go to YouTube and search for xSeriCon. You'll find lots of previous webinars there. And one last thing to mention is we did mention our SIL verification software, SILability, which is much enjoyed by everyone that uses it. It's very smooth and comfortable to use. and does include a built-in failure rate database. So please ask us if you would like a free trial of that software. That's available. Please join us for our next webinar, which will be on the subject of alarm management. That's on the 18th of May. And that's all from me for today. Now we have a question that came. Do you have a proof test checklist to help ensure all tests meet the required standards? Good question. Thank you, Mike. I don't have a checklist as such. I suppose that's kind of partly what I was trying to achieve with the webinar today, was to go run down a whole bunch of points that need to be considered to make sure the standards are met. I suppose such a checklist could be generated. It's something that actually should be covered in the functional safety assessment. The assessor should be checking the quality of your proof testing procedures and training and all of those things. So it might be worth looking at the FSA, Functional Safety Assessment Checklist. Apart from that, I think all I would say is have a look at the textbooks. Yep, so we've just come up with a textbook that we've been working on for a while. This has a section on proof testing. So you might want to have a look at that. I think that's about the best that I could do, Mike, in terms of a direct answer to your question of checklist. Short answer is no, but there's lots of sources of information that could be used to build up a checklist. Maybe Mike, drop me an email afterwards, and we'll see what we can come up with for that. Okay, is there any other question that anyone would like to ask for now? Last call. Okay, in that case, I'm going to close the session for today. Thank you very much once again for your participation, and I'll look forward to seeing you next time. I'll also be sending out the link to the recording. So today's webinar has been recorded, and we'll post it on YouTube shortly, and I'll send you the link. So thanks very much once again. Wish you all a great and very safe day, and thanks again, and goodbye for now.